Okay, click and close, take a look. So real quick for today, Jaden, get in your desk, please. Thank you. Okay, so we're looking at the derivative and kinematics today primarily. So this is where we left off yesterday, right? We're playing this game where I'm going to give you a position function, and you want to find velocity and acceleration. And really the reason being that you're going to find the derivative function, the graph of the derivative of the original function, and then the derivative of that function, right? So that was the first one we did. We said that if I gave you this red position function, what would its derivative look like? Well, you just think in terms of a tangent to the curve. I've got this tangent line which tells me the slope of the red graph starts off being positive and pretty large because it's a steep graph. As we move along, it's getting shallower and shallower, so the value of the slope is decreasing. The derivative, the output of the derivative equals the slope of the function. So as the slope diminishes, the value of the derivative declines until you get to 0. See right there, we've got a horizontal tangent, which means our derivative has 0 value. And then from there on out, the tangents start to get steeper and more negative, right? So we get larger negative values, so the derivative decreases steadily, becoming more and more negative. The acceleration function is the derivative of the velocity function. Well, that's pretty simple. The velocity is linear, and it's got a negative slope everywhere that's constant, and so the value of its derivative is negative and constant. Okay, so we're going to play that game some more. So how about this one? There's the position function. So are there any values that you know for sure? What do we know?
Is the bottom of the curve, is that 0?
Yeah, okay, right. The tangent is horizontal at the bottom of the curve. So down here, at that point, we have a horizontal tangent. So the slope is 0, right? And so our velocity function, which I guess is going to be purple, would have that value. How does the velocity start out? Positive or negative? The derivative is positive? It's negative, isn't it? Because look, here's the derivative up here is negative and a big negative number because it's very steep, right? So that means we're going to get a velocity that's large and negative. When we make it all the way over to here, we've transitioned to a large positive slope, so a large positive velocity. And so isn't our velocity function just doing something like, whoops, that's bad, more like this. Something like that. Everybody see? If we assume that the position is changing uniformly, that the rate of change of the slope is changing uniformly, that's our velocity function then. Anybody see that? So what would the acceleration, the green acceleration function look like? It's going to be flat and positive or negative? Positive, because the slope of the velocity function is constant and positive, right? So we get something like that. Give me thumbs. Does that make sense? Sort of, kind of, maybe? Okay, why don't you guys try one? Oh, okay, so I want to give you a definition before we jump into the next one. So a little vocabulary. So some definitions. Derivative. What is derivative? What is a derivative? A derivative is just a function that outputs the slope of a curve, the slope of a function. The slope of tangents to the curve, same thing as the slope of the curve at values of the input. So derivative is a noun, right? It's a thing in math. The derivative is that function that spits out the slope of the original function, okay? Differentiate, what's that mean? To differentiate, that's a verb. It means to take the derivative. So the process of deriving the derivative function from the original function is called differentiation, okay? So to differentiate is a verb, it's an active thing. It means we're taking the derivative, we're finding the derivative from the function. So then what is differentiability? Differentiability, I guess that's an adjective. Its differentiability is kind of take the derivative ability. Is it, can we take the derivative or not of a function? You might think, well, always you can, but not always. There are some instances where we can't take derivatives, where derivatives are undefined. So when we talk about the differentiability of a function, we're trying to find all the places where the derivative exists and where it doesn't exist. Okay? So there's a really important connection here. I put this in here for your notes. Differentiability implies continuity. That's a huge statement in calculus. We say that, we come back to that one all the time. Differentiability implies continuity. So if a function is differentiable, it is by implication necessarily continuous. If it's differentiable, it has to be continuous. But the converse is not true. Just because a function is continuous does not make it differentiable. And we'll see why. Okay, so there's the vocabulary, right? Those are the important words here. Derivative, differentiate, and differentiability. Okay, let's talk about the differentiability of functions. There are three kinds of places where functions fail to be differentiable, where derivatives do not exist. They don't exist at discontinuities in the function. So if a function is discontinuous someplace, it automatically does not have a derivative there. At discontinuities or other places where limits don't exist. Okay, so differentiability implies continuity. Sharp corners. This is a weird one. We'll look at an example. Any place where there's a sharp corner in a function, it's not, the derivative does not exist there. Okay, that's a weird one. Like I say, it's strange. And then vertical tangents. Vertical tangents, obviously they wouldn't work because the derivative of a function is its slope, and a vertical line has no slope, right? It's infinite slope, so it's undefined. So any place where a function has a vertical tangent, it's also not differentiable. Okay, 4 is a weird one. Cusps are kind of a combination of 2 and 3 put together. A cusp is an infinitely sharp corner. So a cusp would look like this, for example. If we had some function that did that, that would be a cusp. If we had a vertical tangent coupled with a sharp corner, then it's double damage. It really doesn't exist for 2 reasons, but that's a cusp. Okay. So, for example, here, if we take the greatest integer function, at each integer, the derivative does not exist because there are all these jumps in the function at every integer. Okay? Same thing would be true for this piecewise function. Because there's a break in the function, there's a gap where it's discontinuous, the derivative doesn't exist. Okay?
Can I get a note from the teacher?
Yeah. There you go. You bet. So any place there's a break in the function is not differentiable. Okay, what about the sharp corner? Let's investigate this one real quick. So we have like an absolute value function. F of x equals the absolute value of x. Okay, so then, whoops. Think what that does. The absolute value of x is equal to x when x is positive, negative x when x is negative, and 0 when x is 0. Okay, so let's differentiate this. If that's what f of x equals, what's f prime of x? What's the derivative going to be? And we can just see by inspecting the graph what the slopes are. What's the slope of this function for positive values of x? Yeah, it's 1, isn't it? Right? Look at this leg of the graph. I rise 1 and run 1. So when x is greater than 0, the derivative is equal to 1, slope of the function. What about when x is less than 0? Negative 1. Over here we have a slope of negative 1. So what would the slope be at 0? I mean, how could you decide, right? What would it be? An ant walking from the left would expect a slope of negative 1. An ant walking from the right would expect a slope of positive 1. Does that sound right? There shouldn't be a preferred direction there, right? So what do we have to say about it? Does the slope exist? No, it doesn't exist, right? So the derivative is undefined there. So sharp corners, you see how that works then? Sharp corners are places where derivatives also do not exist. Okay, so let's go back to our game. What about this guy? I'll let you guys figure this one out now. What's the velocity function going to look like? What's it going to be? To where? You tell me what to draw here. Do you know any place? Do you know the value at any place or places? What's the value of the slope at x equals 0? Or t equals 0? What's the slope of the red graph at t equals 0? There's t equals 0 right there. What's the slope of the function there? What is it? How come? Yeah. Because it's a horizontal tangent there, isn't it? Yeah. Look, we got a horizontal tangent there. Where else do we have a horizontal tangent? At 10, right there. Right? So those are two places where we know the value of the derivative has to be 0. What's it do in between? It increases. Looks like it increases for a while, doesn't it? The slope is increasing as we move up this. It's getting steeper, 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 steeper. Tell me when it gets to its maximum. Right there, doesn't it? And then it starts to taper off and decrease again. It's still positive, but it decreases back down to, so where it's yellow, it's decreasing back down to 0, right? Everybody see that? Oh, I got lassoed. Okay. So then what would the graph look like, the purple graph? It's going to start at 0. It's going to increase till it gets to 5. And then it's going to decrease until it gets to 10 again. Keep doing that. Thanks. Okay? Make sense? Give me thumbs on that. Does that make sense? Okay, so now that's v of t. What's a of t going to look like? What's the acceleration going to look like? What's it going to be? Straight line, positive or negative? From where to where? From t equals 0 to what? Where does the purple velocity function have a positive slope? Till 5, from 0 to 5. Yeah. It's going to look like, I don't know what the value is, but we'll just call it that, right? It's going to be some, we don't need to worry about the numbers. We just want to get the basic shape down. So we've got something that does that, right? What happens from 5 to 10? Okay, it's going to be negative and constant. What's that? Oh, don't worry about the numbers. I mean, we could figure out, if we actually measured rise over run, we could figure out what the value was, but. Say it again?
Why did you put it at like 3 and -3?
Well, I mean, what is it really? We can see what the slope is. We're rising by 2 and we're running by, but the purple one isn't exact either. Like, you see what I'm saying? Like, we would have to really, like, literally draw tangent lines and kind of figure out what the slopes are, right? So I didn't try to get the amplitudes correct here. I'm just trying to get the shapes right. We don't really worry about to make sure that the actual purple values are the same. All I want you to see is that we're going to get a steadily increasing velocity until we get to 5, and then a steadily decreasing velocity until we get to 10. Make sense? So what has to happen to the green function at 5 then? Does it exist there? Does the derivative of the purple function exist at 5? Say it again? How come? You're right. We said there are 3 kinds of places where derivatives don't exist. Right? No, the purple velocity function was not discontinuous there, but one of these 3 things was happening. What was it? What was going on? It's not discontinuous. What's that? No, there were no vertical. Wasn't it a sharp corner? Yeah. Look at the purple graph. Purple graph has a sharp corner at 5. Right? Any place where there's a sharp corner, the derivative doesn't exist because we'd have different values on the left as we approach from the left and the right. So what that means then is, the point I'm trying to make is that I have to be careful about my endpoints. What kind of endpoints would I have to have in that green graph there? I have to have open endpoints because the green function doesn't exist at 5. Everybody see that? Okay, there's kind of a cool way you can think about this. If you think about kinematics like this, what's Newton's second law? Have you guys talked about that? Probably haven't yet. F equals ma? Haven't talked about that yet? Right, you probably, that makes sense. You may not have gotten there yet. So we know, but you know this intuitively. Force is proportional to acceleration, right? How do you make something accelerate? You push on it to make it accelerate, okay? So always think about this in terms of an invisible hand. So if you look at this original function, if you're picking up speed, like we started off, our position was negative, but the slope was increasing. So that we saw that was an increasing velocity. Doesn't that mean that something would have been, if we're talking about motion on a line at the front of the room where that's the positive direction, the red graph just means that we started someplace at some negative value on our number line. If 0 is right here, we started back at some negative number at rest, and we speeded up in the positive direction, didn't we? Everybody agree? So what's that mean? That means that if we were speeding up in the positive direction, doesn't that mean to accomplish that there would have been an invisible hand pushing on us to make us speed up in the positive direction? Well, the invisible hand that's providing the force is also telling you the direction of the acceleration because they're always the same. Force and acceleration always have the same direction, always. So the invisible hand is pushing us forward for a while, which we can see because look, the green acceleration function is positive from 0 to 5. So from 0 to 5 seconds, I'm getting pushed by this invisible hand because I'm starting at rest and I'm getting pushed forward and I'm accelerating until we get to 5 seconds. And then what happens? At 5 seconds, we're still moving forward, but the rate at which we're moving is decreasing now, right? So that means that the velocity is decreasing. Well, now which direction is the invisible hand pushing on me when we get to 5 seconds? It's pushing that way, right? Because I'm moving in the positive direction, but I'm slowing down. The only way to accomplish that is if I've got an invisible hand pushing me backwards to slow me down, right? Well, what do you notice? The green acceleration function is negative there, indicating that the invisible hand is pushing us in a negative direction. Okay? Are you making that connection? Okay? Let's try another one. How about that one? That's our position function. Any place where we know the value of velocity. At 0, yeah, we have a horizontal tangent at 0, don't we? And so we know the value of the velocity is 0 at 5 seconds, right? Because that's where we have a horizontal tangent. What can you, excuse me, what can you tell me about the rest of it? Is the velocity starting off positive or negative? Positive. Is the velocity decreasing or increasing initially? It's decreasing. And how come again? Tell me why. Okay, good, because the tangents, the slopes of the tangents are getting smaller, right? So we know we're doing something like this. Right? Everybody agree? And again, how come? Because look at these little tangents. They're getting, the slopes of the tangents are getting smaller. What happens from 5 to 10? Okay, the slopes are getting bigger or smaller? Bigger, yeah. Now the slopes are going from 0 up to some positive value, so isn't it just doing something like that? Right? Okay, so what's the acceleration doing then? Which way is the invisible hand pushing me from 0 to 5? Pushing me backwards, yeah, because I'm slowing down. I'm moving in the positive direction, but slowing down, right? And doesn't that make sense? Because look, the slope of that velocity function is constant and negative, so we're doing something like that, aren't we? Agreed? Okay, what about from 5 to 10? What's going on? I'm speeding back up because I'm going from no velocity, right, up to positive velocity. So it just looks like that, doesn't it? Right? Because from 5 to 10, the invisible hand must be pushing me forward. Agreed? Okay, what's this story look like? Well, I start at some negative value. When I start the camera and we start filming it, I'm going pretty fast, but I'm slowing down, and I get to 0, and I stop, and then what? Then what happens? Then I start speeding up again, right? So it pushes me forward from that point. Yes?
So, positive AFT, is that a closed circle or?
Well, okay, so we have to have, we have to have an open circle there because there's a sharp corner in the purple function, and so the derivative doesn't exist at a sharp corner. So that's why we have to have that open endpoint.
Thank you.
Okay. All right, last one. Maybe not the last one. Second to last one. So what about this guy? I put a point conveniently in the middle there. So what's going on this time? Okay, it starts at 0. The velocity does, right? Because we have a horizontal tangent. So the velocity function starts there. It increases, right? Till what point? Till 5, yeah. It keeps getting steeper and steeper until we get up to our maximum slope at 5, and then what happens? Well, I don't think it's supposed to just stay the same then. It's supposed to just continue, right? That steepness, the slope stays the same from that point forward. It's constant. So this is a piecewise function. We had this curve until we get to x equals or t equals 5, and then we just get a linear part of the function. Okay. So isn't that just going to look something like this? It increases till we get to 5, and then what's it do? Then it stays constant and positive. So that would be my derivative function. Anybody see that? Okay. What's the green function look like then? What's our acceleration function look like? No, it didn't every time we did it either. Like it didn't, in that case it didn't. Right? Started with a slope. Yeah. Okay, what about the acceleration function? What's that doing? Okay, positive or 0 or constant or negative to begin with? Straight, and it could be horizontal and positive, right? Because wouldn't you agree we have a constant positive slope from 0 to 5? So it's going to look like, whoops. It's going to look like this. Oh, darn it. Like this. Right, and then what's it do at 5? What's the slope of the purple function from 5 to 10? Ah, so we're going to do this. Make sense? Okay, you getting the hang of this? All right. How about now, this is weird. This time I gave you the velocity function, and we're going to work backwards. Okay, first let's do acceleration, I guess. What's the acceleration look like this time? I want the acceleration. This is velocity. Acceleration's the derivative of velocity, right? Okay, starts negative and horizontal. Good. Till we get to there, and then what's it do? Okay, we got a break in the acceleration because it's not defined there. It looks like that. Okay, that one, no big deal. But now what about position? What in the world's going on with position? Ah, okay, if the velocity initially is 0, what's that mean about the slope of the tangent line initially? It's got to be horizontal. Okay, good. So we'll start, where should I start? At 0? Sure, I'll start at 0. Okay, so it starts off with a horizontal tangent, and then what's it do? Slopes are decreasing. Okay. So I'm doing something like that, aren't I? Right? Agreed? Then what happens? They start to increase back to a value of 0. Aha. Okay. So something like that.
Do we know where it starts?
Okay, there's the question. Do we know where it starts? Or let me ask you this, does it matter where it starts? Does the vertical position of that red function impact its slope at all? Crazy, right? It doesn't matter. This thing could be offset vertically. It could be any place vertically, and it would still work as long as it keeps that shape. So the slopes are the same, right? So we could do, I got to get real tricky here. Let's see, that guy. So I should be able to just do this. I could take that whole thing and just move it up, and it doesn't matter. I could put it any place. The rest of the derivatives don't change. Okay? Make sense? All right. I think that's a good place to stop. I don't want to go any further.